Before we go to the algorithm and getting the solution to a linear system, let's have some notes first. When we say solution, that will be the sequence of numbers that will satisfy each equation in a linear system. A linear system may be consistent or inconsistent. When we say consistent, it has at least one solution. Specifically, it's just either one solution or infinitely many solutions. Unlike with inconsistent, it doesn't have any solution at all. Say we have 5x plus y equals 3 and 2x minus y equals 4. In this video, we will discuss two methods that will be elimination and substitution method. Let's have first elimination. When we use this method, we are to eliminate one variable at a time. And to do that, we have to have different signs of the variable we want to eliminate. Aside from that, they have to have the same numerical coefficients. Having those considerations, in this linear system, it's easier for us to eliminate y first. And yes, that's because our y's here are of opposite signs and they have the same numerical coefficient. And so adding these equations, we would really be eliminating the y's here because that will produce us 0. And so we now have 7x equals 7, and dividing both sides by 7, we now have x equals 1. Let's now eliminate the variable x. Since we want to have the same numerical coefficients but of opposite signs, we have to have a multiplier so that they will have the same numerical coefficients. Let's have this algorithm then. Let's switch the numerical coefficients of the variable that we want to eliminate. That is, for 2 here, let's have 2 as a multiplier for 5, and let's make use 5 as a multiplier for 2. Since both of them are still positive, let's just choose one of them to be negative. Let's now distribute the multipliers. Now we can eliminate the variable x because adding these two equations, we now have 0 for x's, and now we have 7y equals negative 14. Dividing both sides by positive 7, we now have y equals negative 2. Hence, the solution for this linear system would be the point 1, negative 2. If you want to review about plotting points, just click that suggested video. Another way of having this answer, we can actually use substitution in solving y. That is, we can substitute the obtained answer x equals 1 to either of these equations. Say I would choose the first equation. Thus, substituting x equals 1 to that first equation, we now have 5 times 1 plus y equals 3. If you want to recall operations on integers, just have a suggested video. See, substituting the obtained answer x equals 1 to either of these equations would give us the same answer y equals negative 2. Since solution would satisfy each equation in the linear system, substituting the values x and y to these two equations would let us verify if our obtained answers would be correct. Graphically, solution would be the intersection of all the equations in a linear system. Now for this linear system, if we want to eliminate the variable y, we have to have this 3 as a multiplier for this equation, and this has 1 as its numerical coefficient, but then whatever we multiply to 1 will be the number itself. Thus, no need for us to have really 1 as a multiplier for this equation. Let's just make sure that they have different signs, and so let's have -3 instead. Observe that we actually cancel out both our x and y's. In this case, the solution does not exist, or solution D and E. Or specifically, this happens if the left side or one side of the equation does not equate to the other side of the equation. Graphically, when we say solution does not exist, it means that there's no intersection for all of the equations in the linear system. Just like in this example, these lines are not intersecting. Another conclusion that we can make for an inconsistent linear system is that they both have the same slope that makes them not intersecting. So converting these equations into slope-intercept form, we can now see that the slope here would be the same, and that would be the slope is equal to -1. If you want to review about slope-intercept form, just have the suggested video. Now for this linear system, observe that if we want to cancel out or eliminate the variable x, we'll have these multipliers. But then having these multipliers will give us very big numbers. Why not have this? Since 4 can be 16 by having a multiplier 4, let's have a multiplier 4 instead. But yeah, having the algorithm that we had earlier would give us the same answer. This is just another option. Don't forget that we have to have opposite signs, so we'll have -4 here instead. Observe that both of our variables here are being cancelled out. Would we say a solution still does not exist? Apparently not. Notice that this would actually be equal to 0, and so this still satisfies the left side of the equation, which is still equal to 0. And yes, the conclusion for this case would be there are infinitely many solutions. Graphically, when we say there are infinitely many solutions, it means that the lines we are considering are actually just the same.